Good morning, good afternoon. Hello to everybody who is watching the eCHO live stream today. This is episode 171. I'd like to welcome our guest today. Hello. Hi, Shivansh. How are you?
I'm doing good. Good. Thanks for having me.
Yeah, no, thank you very much for being here. To kick things off, if you could give us a quick introduction to yourself and, where you're from,
Sure. Yeah. So my name is Shivansh. I'm the founder of a startup called Loophole Labs. So our whole goal is to allow people to run stateful workloads like databases, game servers, CI/CD, anything that has inherent state on cloud Spot instances. So Spot instances are 90% cheaper. But they come at a massive downside, which is that Amazon can take them away with a 2-minute notice at any given time. So they're same performance, same everything that you would want out of an EC2 instance, but like Amazon can just yank the power, right?
Okay. Yeah.
In return, you get like a massive discount. So what we've been working on for the last couple of years is the ability to like instantly live migrate workloads with no downtime while keeping network connections alive between hosts. And so if you set up to the Spot instance preemption notice, we can get that notice, and then in under about 15 seconds, we can just pick up the workload, move it to another host, don't interrupt the network connections. And so for all intents and purposes, your app stays alive, but you get to run on Spot and get a discount.
I've deployed a bunch of EC2 instances over the years and things like that. I've never really actually played with Spot instances.
Not a lot of people do. It's an odd thing. Like they've been around for a very long time, like for a very, very long time. And they've always been just as cheap. And it's just, a lot of folks think that they can't run their workloads on Spot, which is absolutely true. Like normal workloads have to be designed for Spot, right? They have to be stateless. They have to be tolerant to almost instantaneous node failure. The network plane, or however your clients are connecting to it, has to be tolerant to nodes going away at any given time.
What notification do you actually get then? I mean, hopefully it's not an email saying I'm about to delete your VM, is it?
No, well, so there's two notifications. You can subscribe to the AWS Event Bridge, and you'll get like a 2-minute warning there. That can be delayed sometimes to some extent, and so which is a little annoying. But then the other thing you can do is there's always a metadata service on every EC2 instance. And so you can just curl like the local metadata service that like it's called IMDS or something like that.
Okay.
That AWS provides, and it will just say, "Hey, I'm preempted. You got 2 minutes, right?" So you can just pull it back from the curl request.
Yeah. Okay, bit terrifying if you're running something that's got a long running job on there. Then I guess.
That's exactly it, right? And so nobody wants to run things on Spot, and so to some extent you can. So we use CI/CD, right? It's not mission critical. It's like very easy to see, and so it's one of those things that's actually the perfect thing to run on Spot. 100% Spot. Yeah.
Excellent. Well, I'm super excited to delve into this. Before we do, as we always do on eCHO, just kind of quickly go through the headlines. As always, KubeCon is approaching, and once this KubeCon is done, another KubeCon will be approaching, and after that, and so on and so forth. For time immemorial. I'm super excited for this KubeCon. It's in London, so I don't have to travel very far at all, luckily, to go to this KubeCon. And CiliumCon is going to be part of the co-located events as well. So before KubeCon kicks off, there will be, as I mentioned, CiliumCon, but there'll be Edge Day, there's WASM Day, there's a variety, a huge platform engineering day, because everybody loves platform engineering at the moment. And the schedule's all out for KubeCon EU. Additionally, there has been the schedule release for rejects. So if you don't get your talk accepted into KubeCon, luckily now there is a pre-KubeCon unconference, I guess. Rejects, I've been fortunate to speak at Rejects once or twice as well. And that's managed by, it was managed by the folks at Kinvoke, and now it's managed by the folks at Microsoft. And the schedule has just been released for that as well. So I've had a quick look through, so you don't have to, but there is a bunch of talks around eBPF, a lot of talks around security and networking, service mesh, etc., and a number of talks about Gateway API as well. So if you can't get to KubeCon, you can get to Rejects, where you can effectively see KubeCon quality talks. There. So that's all coming up. We are 38 days out from this KubeCon. So I hope you're all excited. I'm fortunate to be there. So if you are about, you'll be able to find me in the project pavilion, wandering around. I'll be on the Cilium and eBPF booth. So if you have eBPF questions, come find me. Yeah. So that's kind of the main headlines at the moment. I think that's pretty much it for what I wanted to talk about there. I think we should get into it. I'm ready to kind of hear all about what you're doing with VMs and migration and how you're using eBPF to kind of power all of this. Power some parts of it.
Some parts of it. Well, as many as we can. I mean, eBPF is pretty awesome. We've started to put it into places where we didn't think normally it would make sense to it. Yeah. It's so yeah. Okay. So like specifically how we're using eBPF to manage, our virtual machines, it actually comes down to the network layer to a big extent. Our goal, right? Like you said, like it's very scary to run, your databases and whatnot on spot instances, and so to some extent you kind of have to see it working a couple of times before you start to believe that, like, oh, okay, well, this makes sense, right? Like, it's not an analytics thing. We're not trying to predict when the spot instance go down. Like, it is an actual like state machine here. Mm-hmm. There's an actual like event processing thing. Like, oh, if this happens, I'm going to move it here, right? And so, when companies normally advertise, some sort of zero downtime live migration, they don't actually mean that it's live, right? And so for us at Loophole, we need to be able to keep your workload running.
Yeah.
Right. Like that is our like that's number one goal. And so that includes every part of that puzzle, right? And so if I have connected clients, right? Because the other thing is, like, we don't actually know what your workload is, right? To us, a VM is a VM, right? And so whatever's in that VM is whatever the customer chooses there to be in the VM. And so like for us, like the VM is a black box. It's like there's a hard boundary. We don't put anything inside the VM.
So no agents go inside the VM, anything like that? You're not like
we do put like a little like SSH agent into it so that like customers can SSH into this thing. And then we put the ability. So the other thing is, like, there's a downside to a perfect migration, which is that, like, if the application can't tell, and sometimes you actually want the application to be able to know or notify that, like, hey, you've actually moved, right? So there's a little like thing that will run a hook that the customer can provide, and so there's a customizable thing. But generally speaking, like we did. So Dan, I don't think we had the opportunity to meet at a KubeCon. We've actually not had the opportunity to meet in person yet. I am working on it. I know I have 38 days to get myself to London. I get it. But we've given a couple of talks at KubeCon where we've tried to show off to some extent just how far you can go, right? Mm-hmm. Because the core tech is the core tech. It's like I can just pick up a workload, move it from A to B, but like visually speaking, like what does that mean? And so the first KubeCon we did in 2023, we started a Minecraft server, and this is pre-eBPF. So this is before Loophole got into eBPF, right?
Okay.
2023, we started a Minecraft server on an AWS box in Frankfurt or somewhere in Europe, I think. Sorry, on an Equinix Metal box somewhere in Frankfurt. And then we, had the audience members connect to it. And then we picked up that Minecraft server while audience members were connected to it, and we drag and dropped it over to the United States. While they were connected, while they were playing. And so for most of the audience, they were like what actually just happened? And so, we realized very quickly that, like, okay, good infrastructure hides, and it's very like you shouldn't be able to tell, right? And so, but there's a downside to it, which is that good infrastructure hides, and you can't tell what's going on. So during that KubeCon talk, we actually had a customer like approach us like right after and was like, "Yeah, I'm going to pay you." Like, this is our first customer ever. So we're a startup, right? First customer ever came up to us and said, "I love the demo. Like, I love what you guys are doing. I have this exact problem. Like, I have a hard use case for this. I'd love to use you." And we were like, "Great, lovely." And so we're all super excited and giddy because it's, customer came to us. I mean, how often does that happen? That's amazing, right?
That's the dream, isn't it?
That's the dream.
Inbound.
So we have conversations with them, and we realized really quickly that this is not some like small customer. This is a very mature, this is an HPC team This is like a very mature customer. And so the first question they ask is like, how fast are your migrations? And we go 15 seconds. And they go, yeah, that's all fine. Like, how much network traffic can I put into these VMs? And we go, And so we've implemented like, so VM migrations like take different states, right? So to move a VM, you need to move 4 things. You need to move the CPU state. You need to move the memory or the RAM. You need to move the storage, right? So whatever file system there. So that could be like actual folders. That could be a block device, right?
Yeah.
And then the 4th thing you need to move is the network. And so today I want to focus specifically on the network as much as possible, just because that's where all of our eBPF today is, right? So when you're moving a network, there's a lot of different caveats to think about, which is that like customers will not change their clients and customers will not change their backend code. So you cannot touch the backend code, and we already treat the VM like a black box, right? So we know we can't touch that, but then also client code, nobody's ever going to change that, right? And so what we realized is that like all of the magic that we do to make live migrations work has to happen somewhere in between. Okay, and so we implemented a solution to this problem in layer 7 very early on in the life of the company. Actually, in fact, we implemented the layer 7 solution, saw that it worked, and then said, okay, now let's go figure out how to make the VMs move instantly, and we'll come up with techniques on that. Because the thing is, like, vMotion has been around for a while. Chemu has been able to do live migration. So vMotion is like 22 years old or 21 years old.
Is it?
Yes, it's very old. I mean, they've updated it, but I'm saying like the first,
Yeah, I mean, I was a VMware admin in the past, and there is, from my perspective, there is nothing more magical than the first time you vMotion a VM from one host to the other, and like like you always like you're told to ping the IP address of the VM.
Yep.
And you drag it from one node to the next. And you see like a packet drop.
Yeah.
And then you see the connection kind of, and you're like, okay, that's absolutely amazing.
Fine. Yeah.
But typically with VMware as well, though, like the domain is basically the data center. So you have all of these servers, but they're all, and the network is very static. So like, I mean, the IP moves with the VM.
Yep.
Once the network understands the path to the, once it's done all of its ARP updates and all that jazz.
Yep.
It's business as usual.
Exactly. And so, and Chemu does live migrations too today. So like, this is like, we're not the first people to figure out live migrations in any sense, right? What we've done that's special is like, obviously we've made it faster and more commoditized and blah, blah, blah. But our like core like idea is not like new. Like live migrations have existed for a long time and will exist long past, loopholes existence in some form or another. So the big innovation was like, okay, we can move the network connections, because that's the cool part. Like you said, like vSphere, like drag and drop a VM, very interesting, but pinging that is what's important. And so like we realized very early that like after VMware, customers kind of decided, and most organizations in general, even those who aren't our customers, kind of just decided, I don't really want to buy into an ecosystem anymore, right? Like that was a general decision that everyone made, especially now that Broadcom has made it very clear that VMware is not in making mode. Yeah. So we want, we knew that our migrations needed to work in environments where we do not control anything. We don't control the workload. We don't control the hypervisor a lot of the time, right? The client we don't control. So the cloud provider, so IPs we don't control. And so we were like, okay, how can we build on, a something that can take TCP and UDP connection states and migrate them around in sync with the VM migrating? And so it's a very hard problem to solve. Yes. So we started to solve it in layer 7. And so we did this nice demo at KubeCon. Layer 7 is fine up to certain performance characteristics. Like you don't notice, right? It's not like it's always a little bit slower. It's like negligibly slower until you hit a certain, bottleneck, and then it's like, oh my god, this is horrible, don't ever use this. So but that's what we saw. Our first customer ever comes to us and they go, so we use like bonded InfiniBand, like we have these like massive NICs, because they're an on-prem company and they're an HPC company, and so they're like, 400 gig, that's easy. 800 gigs really what's interesting these days. And we're like sitting there like, what? And they're like, so we like max out these NICs, and like we want you to migrate while we're maxing out the NIC. And I was like, oh, and they were like, and also you're not allowed to drop any packets. because
wow.
we use, well, because, you know, think about it. If you're a company who's building an on-prem system, you can assume zero data loss. Like, that is a completely valid assumption to make.
Okay.
Right? Because, like, I'm connecting the wire. What is losing the data? Like, if there's any data packet loss on this system, like, I didn't connect the wire correctly, right? Like, I gotta go replace the part. So they assume to some extent that, like, packet loss is, like, negligible. And so they write their protocols to take advantage of the fact that, like, so they don't use TCP, they like to use UDP, or, like, you know, InfiniBand has its own, you know, various layers that you can use. And so packet loss is not okay, right? Like, and so we're like, okay, so first of all, you want us to go from layer 7 to God knows what layer down to,
yeah, that's
and then on top of that, you want us to guarantee, like, zero packet loss. And so, like, we've gotten pretty close to zero packet loss at the layer 7, which is why the Minecraft server works, right? But it's not like zero. Like, there's a packet loss here or there. And so we were like, okay. So we went back and we became experts in eBPF. Well, because we looked and we said, okay, well, how do you do this? Like, can you write, like, network logic that runs at line rate? Because that's kind of like, but they're not actually saying for it. They're saying, like, line rate. I got to run this at line rate. And so, you know, very early on when you're looking at eBPF, you realize XDP can run in the NIC to some extent, right? It depends on how much, like, the CPU is involved, whether it's using maps and whatnot. But to some extent, your XDP code can be loaded, if you have the correct NIC, can be loaded directly into the network card and run there. And so we immediately went, oh, okay, so line rate, if it's running in the card, I'll make a relative assumption that the FPGA can run it at line rate. And so we said, okay, so we have to do this in XDP. And then so you start looking at XDP and you realize very quickly that, like, XDP is hard, man. Right? Because it's so low level, and because it runs so early in the life cycle of a packet. The benefit of it is that it gets super fast. The downside of it is that, like, there's just not a lot that you can do in that layer, right?
I mean, I've delivered talks kind of on this as well, in that, like, you're doing stuff before the kernel sees these packets, like, and you know, you need to map out the journey of the packet, really, because any changes that you are making, then the kernel's going to see those. And if you start changing things halfway through flows and this and that, the kernel's going to start getting packets that make no sense. And so it's
So, and then debugging is the other biggest issue that we kind of ran into, which is like, okay, well, if the kernel not seeing the packet, how am I debugging what the packet's doing, right? And so for the longest time, like, we had these really odd bugs that we were going through and we were trying to figure out. So yeah, I have some slides that I can use to kind of talk about it if you want to, like, drop me in.
Here we go.
There we go. Okay.
Debugging eBPF is, I mean, I would say, one very useful tool is Packet Where Are You, which is
Guru, right?
It is, especially if you are changing things, because it's really, the kernel doesn't tell you anything. No. It's so irritating. Like, there was something I was doing recently. I was changing some packets or whatever, and no errors. But it effectively, if you knew where to look, I was using Packet Where Are You in the end, and that was effectively telling me that the kernel was dropping these packets because the modifications I was making to them effectively meant that they were kind of out of order or something. But the kernel tells you nothing. It's so frustrating.
No. There's another one actually that's really helpful for debugging, which is XDP dump. So that's really helpful. And then there's like another version of that tool in the same repository, which will tell you what the decision was for the, like, your XDP program. Like, you know, is it redirect? Is it a drop, whatever? It'll tell you that decision. We use that to debug some very interesting issues with VEF interfaces, and I'll go into those. But okay, so the first thing to remember, like, based on everything I'm going to talk about, is that, like, generally, like, live migration is not downtime, zero downtime, right? So a migration for anything is like, I have something running here, I'm going to deploy it to be running here. That I've migrated where my thing is running, right? And so then people came up with live migration. Live migration was like, I'm actually not going to shut down and restart my app. I'm going to pause my app at some point in time. I'm going to move it over, and then I'm going to, like, continue on from whatever, like, point in time that I was at. And so that was, but what people seem to think is like, oh, okay, that just means that my, like, app didn't hiccup. No, I can snapshot your app at times equals 0, and then 30 days later restore it from that point in time. That is still a live migration for all intents and purposes because I did not restart your app, right?
Okay.
A zero downtime live migration is one where we actually don't interrupt your app. Like it's running at point A and then we snap our fingers as now it's running at point B, right? And so, but that's really hard to do. That is very difficult. In fact, I'll go as far as to say zero downtime is actually impossible. You have to have some like network latency and processing time. So to some extent, like what we do, like we target less than 50 milliseconds. So the time between us, like it existing on host A and it suddenly existing on host B, like we give ourselves 50 milliseconds. Sorry, not 50 seconds, 50 milliseconds. So we give ourselves 50 milliseconds.
And that 50 milliseconds is the VM is, I guess, in a non-responsive state? Or
it's paused, right? And so if you look at any of our KubeCon demos, you'll see that during the migration, there's a little network spike, right? And so that's not caused by our network plane. It's all caused by the fact that the VM, like you can't run a VM in two places at the same time because VMs are like, they're not idempotent. Like the moment you do that, their states are going to deviate, right?
Yeah.
You might be doing a random number generator. The CPUs might be different. Like, God knows what's happening. And for us, like actually God knows what's happening because like it's a black box.
Yeah.
Right. So we either run it here or we run it there. And so then it takes time. And so zero downtime is hard because like their state, like GPU state is changing constantly at like the speed of your memory. And so how do you track those changes in a very efficient way? And then when you pause the VM, then you have all this state that you then have to move over. This is not, this is nothing to do with the network. We're not even at the network yet, right? We just have to just move the VM state over and then restore it. And so there's a lot of different techniques to like amortize that time. But if you look at like services like GCP and Azure and AWS, where you can actually live migrate between availability zones, certain instances on GCP, you can migrate between availability zones as well. Those migrations fail if your application is under too much load, right? Like it doesn't take down your app, like it just doesn't migrate it. And the reason it doesn't do that is because, and even VMware vSphere, like same thing, right? There's hard requirements on bandwidth and latency between the two nodes. Those are there because if I cannot move that data quickly enough between stopping and starting,
it'll never get over there.
Exactly. So our biggest challenge was we don't control the hardware. We want this to work at line rate, at when your application is under load. And then like our latency, like we do demos where we're migrating across the ocean. So like a lot of the techniques we came up with were like, can we amortize this to the point where like actually some of these problems are really not problems anymore, right? Mm-hmm. So most folks say like it's a near zero downtime live migration, but like for a database, for example, like no, you got to be zero downtime, right? And then we go a step further now, and we go a step further and we say like, okay, we want network state to be preserved. So like, look, I have some Firecracker VM. We like to run on Kubernetes, but like because everybody's running stuff on Kubernetes these days, right? And so you have some latency between your nodes, and you have clients connected, and so you want those migrations to be preserved, right? Like you want the network connectivity to be preserved, even in scenarios where maybe like the latency is high, and you're going from like Frankfurt AWS to New York GCP, like we did at that KubeCon demo. Like, you need to be able to do these things. So connected clients stay connected, ingress and egress traffic is maintained. So that's the other thing. It's like, let's say I'm talking to a DynamoDB instance. Right? DynamoDB does not understand that I am migrating around. And so from its perspective, like, things were going to break real quickly if IP addresses change or routes change or whatnot. And so all of the like eBPF work that I'm going to talk about today, its job is to solve these problems from the networking perspective. How does the client or the server that I'm connected to not notice? And then how do I, if I'm the client or if I'm the server, how do I not notice as the VM that the world around me has changed, right? So how do you hide that?
Because that's one, I mean, if not obviously migrating a VM generally is a big problem. But for a VM to suddenly go, oh, I'm in Frankfurt and, this networking, it's different.
It's different, and we don't know what's in between, right? Like we don't actually. So we know what's on your host because we can run software on their host, and that's about it. We don't know what the network topology on the cloud provider side looks like. We don't know what the network topology on the cloud, because clients are always on. These are people on their laptops. There's always a NAT, right? Like so I don't know what it looks like, and I don't. The worst part is even if I did know, I control nothing.
Yeah.
Right. And so a lot of what we have to do is based on the fact that, like, okay, if you control nothing, like, what can you get away with? Right. And the answer is actually quite a lot. So this is kind of like a good, like, rough introduction to how, like, we deploy Firecracker on a host, right? This is like, it's a good way. And so I've kind of put this together last night, but generally speaking, you have like a couple different layers. So you have your host, and it's got like some interface. So this, like, Amazon's ENA drivers is doing, GCP's got there, but it's got ETH0, ENS0, whatever. There's a name, and I know why, like, whatever ingress traffic is going to come in through this, packets are going to come in and go out through this. Like, that's the one thing that I'm sure of, right?
Yeah.
And so what we want to do is, like I said, like, we have to isolate your work. The other thing is security, right? Like, you have to think about that to some extent as well. With VMs, like, it's a little bit easier than with containers, because, like, there is a hard kernel boundary, but only to some extent. It's not very just straight up easy. So what we do is we put Firecracker VMs inside this thing called a network namespace. So this is a Linux tool. It's similar to like C groups. We also use C groups to limit like resource units. It's similar to like process namespaces, which is how containers are implemented, right? But network namespaces specifically, they isolate a process from the rest of the networking stack. And so this is done at the kernel level, right?
Yeah.
And so, okay, so I have this network namespace. And so the first question is, how do I get traffic in and out of the network interface? Well, and the answer is the exact same way that you get traffic in and out of the host. You have some Ethernet port, right?
Yeah.
And so in this case, it's a virtual Ethernet port, so a VETH interface, right? And so VETH interfaces are implemented as just like hard-coded pipes. Any packet that goes in on one end appears magically on the other end, and it doesn't go through the kernel routing table. This is really important to remember. I promise you that you should remember this, because I'm going to mention it again and again.
Yes.
And it's going to make up a lot of really interesting things. So one of the things I'm going to give like a good breakdown of everything I'm going to talk about today. But one of the things I'm going to talk about today is like, how do you do XDP traffic? How do you do XDP hooks on egress traffic, which is generally considered not important?
I was about to say, like, most people. So if you don't know, XDP, if you look at any documentation on the planet about XDP, you'll find it says in bold letters, ingress only. Yes. If you want to do egress, then you need to look at TC, because
well, we have hard performance, so we couldn't look at the docs. We have to find a way around it.
If you don't read the documentation, does it even exist? So,
exactly. We put a VETH on the network namespace. Now I could get packets in and out of it. I don't know how yet. Things don't have IPs yet, right? But the next thing we do is then we put Firecracker inside the network namespace. Firecracker has like inbuilt support for doing this. So you can just literally specify the namespace ID, and it will put it in there with like a jailer and a full like isolation layer. And then like within the context of the VM, it does something very similar to VETH, which is like there's a tap interface that exists on the like inside the network namespace. And then any packet that goes into that tap interface appears in ETH0 within the Firecracker VM. So your application sees a VM with an ETH0. Perfect, right? Yeah. And then any traffic it sends into ETH0 appears on tap0. So that's kind of generally how we deploy. And so the next question is like, how do you actually hook up the network? How do you make packets move the way you want them to? And so again, we use XDP for that. And so we put the XDP programs in two spots. We put them on ETH0 and we put them on VETH external. And you'll see I've very clearly labeled ingress and egress traffic. Well, I promise you I will explain exactly how that works. But the thing to remember is, but we'll start with ingress first, right? And so the piece of code that handles networking for Loophole Labs is called Conduit. And so the product that we sell is called Architect, right? And then the project or piece of code that handles all of our networking magic is called Conduit. It's the only like closed source thing today that we have, and hopefully not forever, but that's the only part of our stack that is currently closed source. And so Conduit's job is to modify packets, like at a very high level. And that includes a lot of different things. So that includes encapsulation. So, how do you encapsulate packets in XDP? I'm not going to get too much into that, like not because for proprietary reasons, but just because we'll be sitting here for 3 hours. But I'm we will put a blog post up at some point. We'll walk you guys through how to do that. But how do you encapsulate packets in eBPF without like breaking them up into different? Because eBPF XDP makes it really hard to do fragmentation. Yep. So how do you solve that and yet still encapsulate packets? Like how do you deal with that problem? Our conduit's job is also to modify layer 2 information like MAC addresses. So sometimes we want to route it layer 2. Most often it means changing layer 3 information like IP addresses. And then we actually do touch the layer 4 data, the TCP header and UDP header every so often, because we need to modify ports. So there is a level of like natting effectively that happens in our stack. And we do this for both incoming traffic, right? So it's ingress and outgoing traffic that's generated by the machines. And so the other thing is like, we don't like it when packets touch the Linux kernel at all. Like even outside the context of XDP, because the Linux kernel inherently tracks connection state for security purposes.
Yes, yeah.
Right. And so when you're migrating things around, like, well, if I have an open TCP connection to a Minecraft server and I migrate it around, I'm not opening a new TCP connection. So the next packet that comes in from the client, it's whatever we do to it, it's not going to be a SYN packet. You know what I'm saying? So like the kernel gets very uncomfortable with this. And so we use BPF redirect wherever we can. In fact, we use it everywhere to move traffic between the ETH0 and the VETH interface. And then from the VETH internal to the TAP0 interface. And BPF redirect bypasses the kernel routing table.
So instead of having things like a Linux bridge or having anything like that, you're effectively
our Ingress program literally just goes like, I have a map, like an eBPF hash map.
Yep.
And I'm going to figure out which VETH interface and I'm going to literally call BPF redirect with the like ID of that thing. And then, so like, it's about as fast as you can get it, right?
Yes,
like you can go. And then once it's in the VETH interface, again, when the traffic hits the VETH interface, like it's not considered ingress traffic, right? When it comes here, and the reason it's not considered ingress traffic is traffic coming from the Linux kernel is not considered ingress traffic, and it will not trigger an ingress hook, right?
Yeah.
And so traffic hits the VETH interface, nothing triggers, unfortunately, and the traffic gets passed through, and then it goes to TAP0 because we've hard coded, how to do that. Because where else is it going to go, right?
Yeah.
It goes to TAP0, and then any traffic that the VM generates, goes straight to the VETH internal, and then goes on. I'll talk about how suddenly an XDP starts to work here, but just a little bit of I promise you I will get to it. But there's a lot more context we need.
No, that's fine. It is quite. Yeah, as you mentioned, the fact that you're sending traffic from ETH0 to VETH, I guess external, it's actually outbound traffic, which is very confusing. Like,
yes. Yeah, exactly. And vice versa, right? Like, so you're sending it from one way and the other. And so, so we want to bypass it. Martian packets are usually like the symptom of this. Like if you use the kernel routing table, even if you get the routes correctly, even if you disable IP tables, like, what'll happen is like, we're modifying the source and destination IPs. And so like kernel routing table is going to be like, where is this IP? I don't have a source for this IP, right? And so it's going to be very, very confused. Debugging this is a whole other issue. I will mention one thing. If you were copying us and doing this, which you are absolutely welcome to do, 100%, I encourage it. This is a great architecture that we run in production. It works really well. When you load eBPF programs, you have to specify whether you're loading them in generic mode or not. On certain cloud providers, who shall not be named, Azure, if you don't set them, so you can load the VETH always as native, like VETH as native, like nothing really has an issue with that. But you can't always load the ETH0 as native. And so GCP and Azure specifically, like you, as far as we can tell, like loading them at native for certain machine types just doesn't work. Certain machine types it works fine, but certain machine types it doesn't work. And so if they don't match up, BPF redirect will silently fail. Yeah, and there will be no logs anywhere. The packet will just disappear and go poof. What's happening under the hood is your XDP program is saying BPF redirect, which is a XDP like redirect action, and then somewhere in the eBPF stack it's getting dropped, and because like it's actually not somewhere in the eBPF. I shouldn't say that. It's the driver implementation. The cloud providers are providing for the ETH0 interface. So the ETH0 interface's driver, whatever they're providing, is going, hey, yeah, okay, I have this packet, like I want to send it to this interface, and they don't match because they're loaded at different layers. One's generic, one's not, right? So like the VETH is generic and the ETH0 is not. And so when it goes, it'll just silently fail. So all you have to do, simple fix, took us 3 weeks to find it, but simple fix for anybody else doing this, just always set like the eBPF programs that you run, make sure they're either both generic or they're both not generic. And then the problem goes away.
I'd never come across that before. That is.
It doesn't. It's not a problem if you don't use eBPF redirect. It's not a problem at all. You can just use XTP pass and change the destination IP, and that works. That works.
Okay.
You have to fix the Martian in that case, but
how annoying.
That's Oh, and it doesn't. Sorry, and I should be very, very explicit. It doesn't cause errors from ETH0 to VETH external. It causes errors from VETH external back to ETH0. So this could be a quirk of how we're doing the egress traffic. It could be a quirk of that, but
it sounds more like the driver not implementing.
It's definitely the driver. It's 100% the driver implementation, which is why it's actually weirdly enough not a problem on AWS. And specifically, it's not a problem on certain instances on Azure as well. So we're scratching our heads. We're like, why is it working on this one? And cloud providers, it's very opaque. VMs are very, very opaque.
Yes. Yeah.
So as much as they try not to be, right? So we've just little like tidbit of knowledge that if anybody's trying to do this,
yeah, that's hilarious.
So we're modifying packets. That's Conduit's job, is to modify packets in weird and interesting ways in different scenarios for the purposes of migrating these network connections around without dropping any traffic, right? And so this whole section of today is like, our misadventures in eBPF, right? If you're trying to do a very undocumented set of steps to do a very undocumented and kind of relatively unsolved or impossible problem, like what do you run into? And so the first thing that we ran into is checksum. So like we're modifying packet headers, and this isn't really as important for UDP, but we support TCP traffic. Because we're bypassing the kernel routing table, we cannot expect the kernel to do any checksumming for us. All right, and so we have to do all checksumming, and I will get into why that's difficult, but suffice it to say, XTP does not have helpers for checksumming layer 4 traffic. TC does.
Yes,
it's not available for XTP.
Right.
Then I'll talk about how outbound XTP works. You'll need the context of checksumming to understand that. And then unit testing, actually, weirdly enough. So I'm gonna talk a little bit about how eBPF is actually extremely great for test-driven development. As much as we as engineers hate test-driven development, eBPF is actually like the perfect target for that. And we'll talk about how we implemented that to make testing really easy. So do you have any questions so far, Dan, or do you want me to just jump into TCP checksumming?
No. I mean, it's as you say, it's. I didn't realize. I thought part of the BPF helpers header there was that is yes.
Yeah,
exactly that.
That is there. It's crossed out because it doesn't work in XTP. Like it's not supported in XTP.
Okay. There we go. That's my question.
Which is so like this is the kind of things that you run into, right? You're so early in the stack that like some things just aren't implemented. They're just not there. Some of the common helpers that we're used to just aren't there, right? Yeah. And so uncomfortable truth is like you have to go and figure out these problems.
Yeah.
And so I'm actually going to talk about the implementation. People are welcome to copy paste them, by the way. And so there's going to be code going through here. But the first question we get asked is like, do you do partial checksum recalculations or full checksum recalculations? So a TCP checksum is like it's a very well defined RFC, and I'll talk about the RFC in a second. But generally speaking, like there's two sections to it. There's this like pseudo header that the TCP packet has, which contains actually IP information. I couldn't tell you why they did this. I'm just telling you that like,
yes,
there's the IP header normally, and then you get into layer 4 and why would there be an IP header, IP address information again? It's there. I don't know why it's there, but it's there again. And so it's not in the TCP header itself, but it's part of the checksum. So part of the checksum logic is like, there's this like, you make up that checksum for the TCP. You use the source and destination address and protocol and TCP length as part of that checksum, even though it's not actually part of the TCP header. And then you also use the TCP contents as part of that checksum, right? So we modify IPs, which are part of the pseudo header. So right off the bat, we have to modify the checksum.
Yeah.
But then we also modify TCP ports sometimes, and those are part of the actual TCP header. And so we need to recalculate the TCP. There's no way around it. We have to recalculate the TCP checksum. With traffic control, you have this beautiful helper function called BPF L4C sum replace.
Yep.
And it's really well implemented and automatically calculates partial checksums, full, like it figures it out for you.
I mean, a lot of the functions actually call that as well. So if you're doing BPF SKB, so the Zocchi buffer write or whatever,
Yep.
or store or whatever. So if you change any of the TCP data,
it will do it for you.
Automatically do all of that sort of stuff for you.
But there is no SKB in XDB, right? None of this exists. We kind of ran into this hard wall. All of a sudden, we were like, "Oh crap!" Like our packets are getting dropped by the network because they don't have the correct checksum, because the kernel's not doing it for us anymore. We go, "Crap." Okay, so we need to do a recalculation. First question we ask ourselves is, do you do a partial one? Do you do a full one? For our specific use case, we do actually do partial sometimes, as much as we can get away with it. Sometimes we have to do a full recalculation, right? Sometimes you're modifying so much, like encapsulation, for example, like that is a full, like, yes, you're not modifying the data, but you're adding a header, so everything's getting shifted over a little bit. You gotta modify the data, right? So it depends on whether we're encapsulating the traffic or if we're just modifying the headers, right? But that's kind of how you can think about it. Today, and so I'm going to talk about this like issue a little bit in the next slide, but generally speaking, there is no like standardized, well-defined way as of today to do checksumming. So like we're going to talk about how we did this, but there's this issue that's been open for I think 2 years now, which is an LLVM issue. So it's actually an LLVM issue. The eBPF verifier is actually really, really bad at dealing with checksumming. So I just have the same issue like here. It's really bad at dealing with checksumming code because checksumming, when we talk about the implementation, it's a loop. It's a loop where you want overflows to happen, right? And so the eBPF verifier does not like it at all.
Right. Yeah.
And the other problem is LLVM 14. So there's actually this bug, right? It's specific. It's not an eBPF verifier bug as much as it is an LLM 14 bug, right? LLM does a valid optimization, a completely valid optimization in 14 plus, and which, because it's a valid optimization, like it generates valid ELF code, absolutely valid ELF code. But then when you try and load that program, which we only find out later, so we learned this the hard way, which is that like just because your eBPF code builds does not mean the verifier will be happy about it, right?
It's always confusing. It's like, compiled fine. It's a bit, I feel like Docker
we write Rust code or Go code or whatever. It's like some level of checking happens, and then you go here and you crap, and you're all writing in C, so you don't actually know what you're doing. So yeah, when you try and load it, you get like an illegal access error, right? Like, and it comes down to the fact that there's only many registers the verifier can keep track of at any given time. A loop, and when I talk about the loop, you'll see, but the type of loop that you're doing is like, first, it's inherently unbounded. We've bounded it for our use case, but it's an inherently unbounded operation.
So it can't be unrolled then and things like that, I'm guessing.
Well, actually, unroll also breaks things. Unroll, you have to have a static, right? So on Pragma unroll only works when there's it's not static. It's you were running it across the size of the TCP packet. That's not a static, well-known thing. It's known at runtime, right? So at first we couldn't get any sort of checksumming to work because of this issue, right? We tried everything. And once we realized there was a bug in LLVM, we actually found that the solution to make checksumming work is to have a Docker file. And the Docker file that does all the builds for you, and we pin the LLVM version in the Docker file to LLVM 12. And that solves all of our problems. It generates valid code that loads correctly, like it does all the stuff for us. The other thing to remember is that different cloud providers use different kernel versions, which have different versions of the eBPF verifier. Right. So the verifier itself is also getting better over time. And so what loads on Amazon will not load on GCP. This is a scar, a battle scar. A night before a demo to a customer, for whatever reason, and GCP is not loading our eBPF code. So, we found that like there's this like, basically we use Fedora 38 as the base for the Docker image. We pull in LLVM 12. And that's really all, and then BCC and all the other tools you need, but that's really all you need. And then you can just pass through the folder, call Go generate, because we use Go for our backend, and so we use like the Cilium eBPF library or the Go eBPF library to do it, and then it works. It works great. So just but all the code I'm about to show you, none of it will compile unless you do the Docker build, unfortunately. And even if it does compile through some miracle, it will not load.
Yes.
So the first thing is the L4 pseudo checksum. So what you'll notice here. So first of all, today all the code I'm going to show you is going to be full checksums. That's hard, and then you can go back and remove steps to do partial checksumming. But basically, the way that you calculate an L4 pseudo checksum, this is all based on RFC 1624, which is like computation of checksums. And this is not just TCP, like all checksums in like internet protocol incremental updates are all done kind of during this thing. And so the general idea is you add 16-bit or 2 bytes to a 32-bit or up to a 64-bit sum effectively. And so it's all just additions. You'll see all I'm doing is additions over and over again. And so like what I'm doing is I'm taking inherently a 32-bit number, which is like IP address is a 32-bit. I'm masking off to get 16 bits at a time. And then I'm literally just adding them up. And I do that with the protocol. And you have to do it in a specific order to make everything make sense. But that's literally all it is. So all checksumming according to RFC 1624 is you just add things, and then you have to do this thing called a folding step, which I'll talk about, and I'll talk about how we implemented that. And the folding step converts that like 32-bit checksum back to a 16-bit number because the checksum is 16-bit. Or a 64-bit number. So the implementation I did is 64-bit, and so it works for 32-bit. Right? And so literally just accumulating 16-bit chunks. And so this is the actual TCP checksum, right? So what you do is you take the TCP header. So this is our actual eBPF code. This is what we run. I can't tell you about some of the other stuff, but this stuff, feel free to. By the way, you can replace this with UDP. This works good with UDP. Just replace every invocation of TCP with UDP, and it will work actually just fine. You just don't need to generally check some UDP code. So that's why I'm focusing on TCP here. You can get away with just not. If you just set the checksum field to 0, like
it just goes straight there.
It's fine. Yeah.
Nice.
People assume UDP is lossy and stuff anyway. So okay, so we set the checksum to 0. We have this 32-bit number. We go and we do the pseudo checksum. We have our TCP header that we've already modified, right? We've already modified the IP header. We have our TCP length. Those are the 2 pieces of information we need to calculate the pseudo checksum. And then we need to do like very strict bounds checking because we're about to for loop over the packet size, which is an unbounded, and eBPF does not like that. And so we have a max TCP packet size. What we realized was that like the eBPF verifier can only go through so many branches. And so if your max TCP size is actually too big, this loop is actually too big. And the eBPF verifier will say, no, I can't verify this. Not because it's invalid, but because it branches too long, right? It just so happens we got really lucky with this that the maximum eBPF supported size per packet for XDP is like 3840 bytes. I have no idea how Amazon calculates that, but that's the maximum that they have. And so if you subtract the TCP header size from that, you get a perfect packet size that actually is small enough for the verifier to understand. So that's how this packet is 3840 minus the size of the TCP header struct. That's kind of what we put in.
There's an issue with like MTUs and XDP in terms of there is a reason why it's 3840, and I'm going to try and find it.
Okay, I would love to know. We don't know. We just kind of.
It's in the Cilium docs somewhere because it's a setting as part of Cilium because it is also
really
So there is reason for it, and it's in the Cilium docs somewhere.
Okay, I would love to know that. And then you can see like what we do is we go through the packet content and we literally just add 2 bits. So you can see what we do is we take packet size divide by 2, and we cast it to a. So the buff, if you look at buff, is a U16, right? And so that's 2 bytes or 16 bits inherently. And so every time we jump by 1, we're actually jumping 16-bit chunks at a time. And so we're literally just adding a 16-bit chunk to the sum and then jumping forward 16 bits and doing that over. So it's exactly what we were doing with the L4 header. Now, you need to, for whatever reason, just to make the eBPF verifier happy, even though you have a bounds check for the data end, like you've already done that, you need to check it here. Like nothing really that you can do about that. And then you also need to check it here. And so the reason you're checking it here is because like right now we're making an assumption that the entire packet size is aligned to 2 bytes, which it may not be. And so it might be 1 last byte left over. And so this whole thing lets us check that. And it's written in a way specifically to make the eBPF verifier happy. Even though we have validated the bounds check here, and we have validated this max packet size at the very beginning, because of the way eBPF works is because there's a loop in the middle of it, it will lose track of that fact. And it'll lose track of the fact that it has already validated this. And so you have to just do the check again. And it's what it is. And so, okay, again, I've added a bunch of things, and now I just have to do the fold. And so, let's talk about the fold. Fold is really simple. I can unroll now, right? Because it's 4, right?
Yep.
And folding is literally just that. We just take the 16-bit parts of the 32-bit number or the 64-bit number, and we just literally add it together. Yep. And we take the ones complement, and that's it. That's all you. So this is all according to the spec. But all of this code is written in a way where if you use LLVM12, it will compile, it will load across all the cloud providers. That's kind of like the important part.
Okay. Yep.
Okay, so that's how you do checksumming in XDP. It's a little bit annoying. Those are the functions you need, but this is valid, and I'll tell you how we test that it's valid as well, afterwards. But this is kind of the important piece. So, okay, now for the thing that I know, Dan, you've been waiting for. How do I run on network traffic? Okay, so this is novel, or we think it's novel, but the implementation is actually kind of straightforward, and frankly, it's a little bit dumb. So think of the requirement, right? We need to modify packets like coming in both directions, right? So ingress, egress traffic. Incoming is easy, right? XDP will just do that on ETH0 for us. Normally for outgoing traffic, you use traffic control. But our code base is set up for XDP. So even though we could, and we need performance and blah, 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 we could have done it in traffic control. Like I'm going to make up a reason why we didn't, which is performance. And I completely believe it's valid. Practically, you can get away with TC. But we didn't want to. We were like, no, God damn it. We want to be able to do this. Okay. So, and we also don't want to parse the TCP data. Like customers they get weird if you parse their packets, even if, so we're like, okay, we're not going to do any of this. So, to do this, okay, you need two things to run eBPF XDP hooks on egress traffic. You need two things. You need network namespaces and you need VETH interfaces. And so you can look that inherently the way Firecracker is set up, or at least our Firecracker is set up, is we have network namespaces and we have VETH. And what you need is all egress traffic has to originate inside the network namespace. This is the very key piece that you have to remember. Okay.
Okay.
Which for us it does, but you can just get the traffic. So you can actually have two VETH interfaces. Like you can have this VETH here, you can have another VETH, and you can get traffic into the VETH and then like send it back out this VETH, and this will still work. It just has to come from the kernel routing table within the network just has to drop a packet into VETH internal. As long as that very specific requirement is met, you can run eBPF function on XDP. Because think about this, and it took us a while to figure this out, but when the packet comes in from the outside world into ETH0, the only thing that the eBPF stack is seeing is that a packet has appeared and it didn't come from the kernel routing table. Okay.
Yep.
The way VETH is implemented, there is no kernel routing table between this and this. So any packet that enters VETH internal is not going through the kernel routing table and entering VETH 0. And remember, VETH external, they try and reuse as much of the actual Ethernet code as they can, right? Which is a good code practice. And so if you do the correct steps, I'm about to walk you through the correct steps.
I like
you can attach a standard XDP program with no changes to this VETH external interface, and any traffic that is generated from within the namespace and sent into this VETH internal will trigger the XDP hook. It will absolutely work. Now, you have to do one of two things to fix the problem. Number one is you have to enable GRO on your VETH internal. So that's option number one. And in full honesty, we have no idea why that is. We found this old talk from a very long time ago by one of the maintainers of eBPF, and it's not written down anywhere for whatever reason. It's just in this talk. We'll publish a blog post. We'll write it down somewhere. We'll make it indexable. But you have to run either a dummy VETH program here. So that's actually what the talk said. It said you have to run a dummy XDP program, which will do nothing and actually never get triggered because, then actually it will get triggered from here to here, right? Because it works the same way, but it's not going to do anything. And then when, traffic is generated from the VM and goes into VETH internal, it won't get triggered. But it being there, or if GRO is enabled, will, for whatever reason, make this whole trick work. And this works across the cloud providers. So we test across Azure, Bare Metal, GCP, and AWS. Every day we integration test. This whole thing works in that environment.
I love this. This is very clever. It's
right.
It's clever. It's sneaky. I think.
It's sneaky. Well, you know what? The best solutions are sneaky. And the beauty of this is this is not limited to us. All XDP hooks will work this way, right?
Yep.
They should just work. And so the packet goes into the VETH internal. and it triggers the hook. And then we use BPF redirect to make it appear from here to here, right? And this is not a map lookup anymore. This is just hard coded. We know at startup, we know the ID of each zero. It's not really changing, right? Yeah, so things will work great. So remember, GRO or a dummy interface on Veth internal is a hard requirement, and then you can load an XDP program on Veth external, and now you can do outbound traffic. And so your process can live within the network namespace and generate traffic that way. That's fine. Or you can use a bridge or something to get the packet to go through and just take a route through the network namespace. That's fine too. There's an overhead to doing that, not a lot, because you're not really leaving the Linux kernel. You're not coming up the user space. But there is an overhead just to be aware of. So we like to, for us, it's fine because we generate the packet here. So there's no additional hop, right? It doesn't have a choice. It has to go through the Veth. So we got lucky to some extent that our architecture maps.
So to bring this in here. Hi, Samuel from Brazil. I'm glad you're enjoying this talk as much as I am. Just like I think this is, as I've mentioned, some very clever, sneaky eBPF magic that's taking place. Quickly, also, hello to Tony, and hello to Joseph. So yeah, thank you. Carry on.
Okay, all right. Okay, now I'm gonna talk about something that maybe is not as interesting, or maybe it is more interesting. For us, it was not interesting right up until it was. So like when you're writing a POC, things are very, very interesting, and then eventually you get asked, well, how do you test this? And then everyone's like, well, maybe we do. And we didn't. Look, we're a startup, right? Initially, we weren't testing things back in 2023. Last 2 years has been a lot about like testing and deterministic simulation testing, fuzz testing. And so one of the questions we asked ourselves was like, how do we test this XDP code? And so if you look online today, a lot of the like state-of-the-art testing happens at the integration level. Like I'm going to spin up some lab nodes and send traffic and make sure they do the correct thing, which is not bad. We do that too, right? But when you're developing these very complex, so like today, like here's what Lupo's working on today. Today, we're trying to implement encrypted VPNs in XDP, line rate encrypting VPNs in XDP, which means we have to bring KTLS functions into the eBPF, into the XDP hook, which you can do now. There's a very recent like thing that lets you do that. It's a little bit annoying to implement, but you have to do the handshake outside, and so it's annoying. It's a little bit of like a handoff period, but but once you've done that, right, like you can go in and you can have like an encrypted point-to-point VPN implemented fully in XDP where the traffic actually never has to come up into the user space. Super helpful for performance, right? And so like when we're doing things like this, it's not actually just about testing at the integration level. Like you have to unit test your code. And so what we realized, and what I guess the eBPF ecosystem also realized, was that because these are single stateless functions, that's exactly what they are, right? XDP hooks at the very least are like, as well as other eBPF hooks, but they're all stateless single functions. They don't carry state between them. They're the perfect thing to unit test and have test-driven development. You have like XDP is a black box from the perspective of the kernel, so you can treat it as a black box while you're developing. You can say a packet that looks like this is going to go in, and the packet that comes out has to go like this, and here has to be the routing decision. And so you can write a bunch of tests that do that, and then you can write your XDP hook and make sure it does things in those different scenarios. And so, as if the BPF gods were listening to us, there is a syscall which will take an XDP hook. So the way this like BPF syscall is implemented, it will run the XDP program. And instead of running it in the context of like a packet coming in from an external interface, it will just take in a slice of data, and it will call your XDP hook, and then which will modify that slice of data, which is a packet, right? The slice of data should represent the packet, and then it will return that, and as well as the action that your XDP program returned, as well as an error if there was actually. So like, but this is great that it'll do that in theory, but like, how do you actually use that, right? And so our good friends at Cilium have been nice enough to implement this in Golang, because we use Golang, right? So the Cilium eBPF library has a really nice helper for this, where it does exactly what I said. It takes in a slice of bytes, and it calls your eBPF program, your XDP. And so this will work for other eBPF, but for XDVM sake specifically, if this is an XDP program, it will take that, it will pass it in. This has to represent some packet in a serialized format.
So headers and everything.
Yeah, and I'll tell you how we generate those. There's actually a really easy way in Go to do that.
Yeah.
And it will return the like action that you took, as well as the modified slice, and then an error if one occurred. And so how do we use that? There's a library from Google called GoPacket. And so we've written our own. So this is our helper function that we've written on GoPacket, where like we take a packet, we call serialize on it, which we use GoPacket to then go and serialize this into bytes. We literally call program.test. We get the modified slice out, we decode it, we turn it back into an XDP action enum. Like that's all this helper really does. And now we get, so this thing returns the modified packet decoded, right? So as a struct, it returns the XDP action. And so now your test-driven development looks like this, where you go, I'm going to run an XDP test with so this is one of our like DNAT programs, right? So the destination NAT. And it takes in some packet in a structured format that we understand. It takes my eBPF program, it calls it. I validate that the action is a redirect, and this is just our docs, right? And to figure out what's going on in this case. And then we literally go and we can validate each different thing. Now, we could just compare the bytes to something, right? Like there's no reason that we have to decode the packets. But if we decode the packets, you can find exactly where the bug is. Right? Yeah. And so you can see the GoPacket library has a generate checksum helper for us. So nice of them to do that. And we feel very comfortable trusting Google's implementation of checksumming. And so all we do is we validate the L3 and L4 checksum against what our eBPF program returns. So this incoming packet does not have a valid checksum when it goes in. It's set to 0. And then we go in and we just make sure that, it is calculating it exactly how we expect. And so now you can write 500 tests like this that all run very quickly, relatively speaking, and you have like a perfect test-driven development environment. And so now that we're implementing all this stuff, like we're going back and we're touching that checksumming code, we're making it faster, but we don't know whether it's valid. Now we know whether it's valid. We don't have to go through the whole integration test.
This is excellent. Like I don't think we've ever done a talk actually on eBPF unit testing. So this might be the first time a lot of people are actually seeing. And I mean, I've written quite a bit of eBPF code, I suppose, and I have yet to write a single unit test. So like now I know how to do it. So like that's, and also the GoPacket library is great. So, I mean,
it's great.
You can wrap. Here's my layer 2 headers. I'm going to add those on and blah 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 blah.
Yep.
And then have it just basically create for you a frame basically,
and that's exactly. And so the nice thing is like because it does all that hard work for you, you can then go and validate every layer, right? So like we validate layer 2 because we do modify that sometimes. Like there are decisions that get paid. We validate layer 4, layer 3. Like we go through each step and we go like, okay, are we making bugs here? So much easier to iterate now because you just call go test and it goes and takes your newest eBPF program and fingers crossed it works, right? Okay, I think that's everything I have for today. I mean, I've taken up an hour here. If I go into the next thing, we're going to be here for another hour.
I mean, this has been absolutely fantastic. It's been an absolute pleasure to hear about everything you're doing. And like, I've learned. I love doing the eCHO shows. And a lot of times I'm kind of amazed and stuff like that. It's been a little while, I think, since I've been like, oh, I didn't know that. I'm learning from the community and I'm learning from people who are doing, I mean, the XDP egress is absolutely amazing.
So actually, I want to make sure I give credit here. So one of our engineers, Alex Sorley, he is the one who came up with that. Actually, I'll go one step further. He's the one who came up with all of the tips and tricks. He figured out unit testing, and so he couldn't be here today. He should have been the one giving this talk, honestly. But we'll make sure we get him to write some blog posts that go and
look forward to reading.
But yeah, so I just want to make sure he gets the credit for banging his head against this for the last couple of months.
Yeah. There is a lot of head banging when it comes to eBPF as well. But,
it is a uncomfortable until now. See, now we're comfortable with it, right? Because we have the unit testing, we have all that. So you make a change, it's not as much of a black box. But like even now, like we'll run into bugs where like. We ran into a bug a few months ago where like a packet was disappearing. You have to go drop into packet. Where are you? And XDP dump. And there's another.
Well, I mean,
Red Hat, but
there's that. But I mean, I'm just going to move my structure around. Like verifies like, no, I'm not happy now. Like, well, I've done from
we learned this the hard way. But another interesting thing that Alex figured out was sometimes you have keys and values for you define your struct key and value for your XDP maps, and that I think like eBPF is like really powerful once you have maps involved, right?
Yep.
They have to be a minimum size. So the Golang eBPF library will add padding.
Yes.
C will not. And so for a very long time, so it will compile fine without the padding, and then you'll run into really odd bugs. So you actually have to add like unused padding, to make sure everything gets aligned. It makes no sense at all. Yeah, it's one of those things where like you don't see it until you do.
There is a keyword I think you can put in your eBPF program for it to actually sort that out. There is, because I actually had to do. That's gonna bug me as well. I'm gonna try and find that as well.
Okay, that'd be great.
Right. Anyway, thank you again for your time today. That was absolutely amazing. Thank you everybody else for joining. If you're watching us live or if you're watching a recording of this, again, thank you for watching that. Thank you. Thank you again, Shivansh. And
thanks for having me. Yeah, it was great getting to talk about this finally.
yeah, absolutely. Hopefully I might see you in 38 days.
I'll do my best.
Anybody else who is at KubeCon, please, if you want to come talk to me about eBPF, I will love to listen to or try and answer any questions. And with that, it is goodbye from me.
Thanks for having me.
All right, cool. And we'll see you all next time. Thank you.